The improvement process can be represented by a scheme resembling a branching tree, whose thick trunk gradually splits into smaller and smaller branches as it rises upwards. Each of the first thick branches splits into several thinner branches. Then, at a greater height, these branches split into several even thinner ones, and so on. The trunk of this tree represents the initial stage of a phenomenon or object before the process of improvement begins, and each branch represents a specific feature that is gradually changed, increasing the overall effectiveness of the phenomenon or object. Going from the bottom to the top of this scheme would show progress and improvement, with the highest number of branches at the highest stage. In the initial stage of the phenomenon, only a few different characteristics can be identified that can be improved. And then, as the improvement process gains momentum, more and more additional minor features appeared for further improvement. Because during the improvement process, the amount and accuracy of available knowledge about the phenomenon in question constantly increases. And observing the performance of its functions, the amount of information about its connections with elements of the environment also increases, and it becomes much clearer what else could be changed in order to further increase the efficiency of the phenomenon. If, during the process of that phenomenon's improvement, completely new properties are discovered whose development would contribute to the overall progress of that phenomenon, they would be represented in the scheme as new branches extending from the trunk with the names of those specific properties. And if new properties are discovered by modifying previously discovered properties, then they would be marked in this scheme as additional thinner branches splitting off from the previous branches that represent the properties from which they originated. The more each specific feature is explored, the more we learn about the different smaller aspects that make it up, which have potential for further improvement. And the more different aspects are developed at the same time, the more the overall improvement of the whole process gains momentum. For example, in primitive communities, when some kind of material was needed for certain purposes, and it was too large in size, for example, wood for building a house, individuals had to find suitable ways to break it down to a size that could be lifted by their own strength and used for further processing. In the beginning, people were breaking and dismantling it using only their physical strength, without any additional means. This process could be attributed to the initial stage, which, in the improvement tree scheme, would correspond to the trunk, calling it crushing of building materials. However, this method was very slow, consumed a huge amount of physical energy, and, for that reason, was very tiring and caused various injuries and traumas. Therefore, in order to make this work more comfortable and less painful, people came up with the idea of using some kind of external object from their environment that would not cause pain or damage the skin when coming into contact with a working material, and decided to do this by striking it with various hard objects, such as stones, flint, bone. And notice that this made the work much easier and more efficient. This event would mark the beginning of the improvement process, taking the first step towards progress. And in the scheme, it could be marked as an extension of the trunk upwards, calling it creation of working tools. Later, while experimenting with objects made of various different materials, people discovered the first and one of the most important properties necessary for increasing the efficiency of the crushing process: hardness of the working tool. And from that time on began to search for the hardest objects in their living environment. For this purpose in the scheme, this process could be represented as one of the first branches splitting off from the trunk, calling it knowledge and application of hardness. Later, over time, people also noticed that stones with sharp edges helped them to do their work faster than those with a smoother surface. And from this, they assumed that the sharp edges of the work tool were probably responsible for this. As a result, to verify the accuracy of their assumptions, they began to sharpen their work tools to maximum sharpness with their own hands. This confirmed their assumption, because the sharper the tool was, the easier and faster it could chop the building material. In this way, through working experience, people learned another important feature that helps to further increase the efficiency of crushing process: sharpness of the working tool. This was another step forward in the process of improvement, as the use of these two features at once made it possible to achieve even greater operational efficiency than when using only one of these features. The first axes were created using these principles. This step could be represented in the scheme as the second branch extending off from the trunk and called knowledge and application of sharpness. Later, upon discovering some other new feature that could further increase the efficiency of the work process, it would be represented in this scheme by a third branch extending from the trunk, and so on. Meanwhile, as they kept exploring the sharpness property further, people noticed that the efficiency of cutting process depends not only on how sharp the tool is, how thin the blade is, but also on its spatial structure. For example, people have noticed that a tool which blades cutting surface has some kind of irregularities, for example, in a form of a spike, hook, etc., helps to perform the work a little bit faster and easier compared to a tool with the same degree of sharpening but with a flat blade surface. This stage of the improvement process could be represented in the scheme as a new thinner branch, branching off from the knowledge and application of sharpness branch, with the name knowledge of spatial structure of the tool's blade and application in the crushing process. Having discovered this property, people began to make tool blades with the sharpest protrusions possible. Soon, people noticed that blades of this shape were much easier and more convenient to work with when rubbing them against the surface of the working material with longitudinal movements back and forth. In other words, sawing the material rather than chopping it. This step can be represented in the scheme as another new branch, coming off from knowledge of spatial structure of the tool's blade and application in the crushing process branch, giving the name for that new branch knowledge of the working movements, manners, implication to cutting process. Based on these two principles, the first hand saws were developed. When examining this characteristic, it became clear that not only the manner of the movements, but also their speed is important for the efficiency of the cutting process, because the faster the tool blade moves, the less time it takes to cut the required piece of material. This new step in the improvement process could be marked in the scheme as a new branch, extending from the knowledge of the working movements, manners, implication to cutting process branch, and calling it knowledge of tool blades movement, speed, impact to cutting process. Therefore, much later, when various engines were invented for industrial and transport purposes, a similar principle was devised for use in the field of cutting tools in order to achieve the highest possible speed of the tool blade's movement with the smallest possible operator's physical efforts. Based on these principles, motor saws were invented. And, speaking of further improvements in the hardness property, there have been no significant changes in this area for a long time, because in order to increase the hardness of materials artificially, much more knowledge was needed about the physical and chemical properties of materials, and it also required a significantly higher level of technological development. Thus, in the distant future, people, while experimenting with physical and chemical properties of various materials in certain ways and for certain purposes, noticed that fusing certain materials with each other resulted in the creation of materials with significantly greater hardness and stronger structure than the original materials used in their production. For example, combining carbon with tungsten produced tungsten carbide WC, which is significantly stronger than both carbon and pure tungsten. As a result, people began to mass-produce such materials and use them in areas where maximum strength and durability are required, such as construction and the manufacture of various tools, including cutting tools. By using harder materials for the blades of cutting tools, it became possible to cut significantly harder materials than before, and they didn't wear out so quickly. This stage can be represented in the scheme as a new branch splitting off from the knowledge and application of hardness branch, with the name knowledge about the interaction of different materials in creating new substances with greater hardness. However, this branch should be stretched out quite high in the scheme of improvement tree, as it took a long time for people to finally acquire enough knowledge about this feature to be able to use it properly. Much later in the future, people invented laser beam generators and discovered that they could also be used in the cutting process, because when a high concentration beam of laser rays is directed at a single point on the surface of a material, a very high temperature is generated at that point, which is sufficient to break the physical and/or chemical bonds between the particles, creating a crack in that place, i.e., the material is being divided into two separate parts. Of course, this also depends on the power of the laser beam and the hardness of the material being cut. Isto é, the destructive force of the laser beam should be greater than the attraction force between the particles of that material. Initially, When the laser was first invented, it was intended for scientific experiments, but later it began to be used in medicine and other fields. And only later, people also found ways to apply it to the cutting of various materials. Thus, it can be said that the invention of the laser does not belong to the above-described scheme of crushing a building materials process, since it originated in completely different fields, which were unrelated to crushing. The laser's ability to break down solid objects was discovered much later, when it was found during various experiments that certain types of rays can generate extremely high temperatures, and this property began to be used in the development of the latest generation of high-efficiency cutting tools. Thus, the original invention of the laser would belong to a separate improvement tree scheme from which one of the branches describing the laser's ability to generate high temperatures and use them to break down solid objects would connect with the improvement tree of crushing process scheme. According to this example, it can be assumed that even seemingly completely different spheres are interconnected in certain areas, and therefore they directly or indirectly influence each other during their activities. This could also be schematically represented as a huge forest, where each individual tree would represent a specific phenomenon or object with all its current progress. And each of these trees would be connected to all the other trees in the forest in certain areas of the branches, forming a dense network of branches. Each of the branches connecting one tree to another would represent a specific property that directly or indirectly affects the process, represented by the other tree. And the manner of that effect would determine which branch would be connected to it. Isto é, which characteristic will be changed at some degree under the influence of the characteristic of that connected process. This also confirms the hypothesis mentioned in previous topics, that all phenomenons in the universe are somehow related to each other, and therefore various changes in one or another phenomenon have a certain effect on all other phenomenons. So, in summary, this improvement tree scheme can be applied not only in primitive spheres, such as the production of tools for cutting, hunting, or building settlements in primitive communities, but also in modern spheres of contemporary society, such as the development of transportation, computer, and robotic technologies, as well as other areas where it is possible to improve operational efficiency.